increases and is maximum and then starts decreasing. That point is called as inflection point. We draw the tangent at that point, and from that we take the measurements of LT, delta Cp, and then calculate n the reaction process reaction time. Okay, so these are the calculations then, and then by trial and error basis, the Ziegler and Nichols gave the controller setting for proportional, integral, and derivative. Okay, so these were the settings, and these were the normal standard settings of PID controller. If we want to satisfy the quarter amplitude criteria, Cohen and Kuhn then suggested some corrections in this original standard settings. He defined R as log ratio NL divided by delta Cp, and then he gave some corrections. With these corrections, then we can obtain the PID controller tuning for quarter amplitude criteria. Okay, so we solved numerical examples, two examples on the basis of this. If the process reaction curve is given, how to draw the tangent at inflection point, how to measure L and T and delta Cp, calculate N and R and all. Okay, so we already done this. Okay, now let's start the second method, Ziegler-Nichols method. Okay, this method is also called as ultimate cycle method. Okay, here what we do in this method, Ziegler and Nichols suggested that the system is set into oscillations, deliberately set into oscillations. Okay, so and then two quantities are measured from these oscillations. One is called as ultimate gain or critical gain, and other is called as ultimate time or critical time. So the critical gain Kc and critical time period Tc, these quantities are found, and from that again Ziegler and Nichols prepared a table, or rather gave the setting for standard PID tuning. This was way back 1964 rather. Okay, so again for quarter amplitude criterion, Cohen suggested the corrections in this method also, and uh, with those corrections, the method gives the PID tuning, PID controller parameter tuning for quarter amplitude criteria. Okay, and see this method is suitable for systems without self-regulation. We saw in the first method, a transient response method or process reaction curve method was suitable for systems with self-regulation. Ziegler-Nichols method or ultimate cycle method is suitable for systems without self-regulation. Okay, so step-by-step procedure for conducting Ziegler-Nichols test on a process, okay, are like this. Okay, where it is. So these are the steps. For the first step, the integral and derivative actions, that is Ki and Kd, whether Ti or Ki, and Td or Kd. Okay, these are kept as minimum. Right? First thing, so only proportional control will be active. Both integral and derivative controls will be inactive. Right? So this is the first step. It is ongoing process rather. Okay, process is running, and what we do, we ongoing process, we adjust the integral and derivative actions to its their minimum. Okay, and gradually begin to increase the proportional gain Kp. Okay, Up to what point it is increased, then Kp is to be increased up to the point where the system starts small oscillations. Okay, a continuous consistent of oscillations are started. Okay, the system begins to oscillate with a small period. Okay, so the proportional gain is increased to that extent. The oscillations are started. Okay, as soon as the oscillations are started, that gain Kp, proportional gain Kp, when the oscillations begin, is called as a critical gain Kc, right? So note the, and this critical gain Kc is noted down. Note the critical gain Kc at which the dynamic variable just begins to exhibit steady cycling or oscillations about the set point. Okay. Similarly, at this point, when the oscillations begin, okay, find the period of oscillations, okay, time period of the oscillations, and this time period of oscillations corresponding to uh, critical gain, okay, is called as the critical period Tc. So, what the important steps are? We adjust the Ki or Ti to its minimum. We adjust Kd or Td to its minimum. So both actions are negligible, eliminated, and only proportional action is existing. Okay, and in that we increase the proportional gain Kp to such a point that system start oscillations, and then that gain that gain is called as ultimate gain or critical gain Kc. Similarly, the period of these oscillations is called as ultimate period or critical period Tc. So both of these quantities are noted down, and then Ziegler and Nichols then suggested, it's by experience. This formulae doesn't have any mathematical base. It's just trial and error, and from the experimentation, they then on the basis of Kc and Tc, they suggested some tuning parameters for Pi and D. And Ziegler-Nichols gave the setting for PID or various types of controllers, PI and PID, as in this table. So if only proportional controller is to be used, then Kp should be 0.5 into Kc. Kc is the ultimate gain that is already recorded. Or if it is proportional plus integral PI controller, then Kp should be 0.45 Kc. Okay, whereas the integral time Ti, which is 1 by Ki, okay, is given by Tc, that is measured already measured critical time, critical period, sorry, Tc divided by 1.2, right? If it is PID controller, then Kp should be adjusted to 0.6 times the critical gain, whereas Ti should be adjusted to critical time Tc divided by 2, and Td is given by critical time Tc divided by 8. So with these settings, the system can work properly. Okay, these are called as the standard state PID controller settings. Okay, which were given by Ziegler and Nichols. Okay, can you hear me? Am I audible? Na? I'm continuously talking. Am I audible or not? Am I audible or not? Anyone? Okay. So let's continue. I forgot to confirm first at the start. Okay. So these were the settings suggested then by Ziegler and Nichols. Okay. Again, for quarter amplitude criteria, what is quarter amplitude criteria? The every peak should have amplitude 1/4 of the previous peak. So this was the so that the oscillations will die down at the faster rate or optimum rate. Okay, so for quarter amplitude criteria, Cohen and Kuhn again suggested some corrections in the settings given by Ziegler and Nichols, and those are like this. Okay, so settings for quarter amplitude response. For proportional control, if only P is there, then Kp is adjusted until quarter amplitude response is obtained. So gain is increased, there is no formula. Gain is increased until that quarter amplitude response is obtained. Okay. Whereas if it is Pi, then Kp is given by 0.45 Kc. Kc is already measured during the test. Ti is equal to Tc. Okay. Whereas if it is PID, then Kp is 0.6 Kc. Pi is Tc divided by 1.5. Td is Tc divided by 8. Okay. So these are the settings. So let's solve one example based on this one then. What is the problem? In application of Ziegler-Nichols method, the process begins oscillations with 30% proportional band in an 11.5 minute period. Okay, find the nominal three-mode, nominal that is standard, nominal three-mode controller settings and quarter amplitude three-mode controller settings. Okay, three-mode means PID control. If it is two mode, generally it is PI. If it is one mode or single mode, it is proportional P. Okay, both are three mode asked, and therefore, in both cases, nominal or standard three mode controller setting, PID control settings, and PID controller settings for quarter amplitude response. Okay, so in both cases, P, KP, Ki, and KD are to be adjusted. Okay, what is the proportional band given? Proportional band is given by 100 by Kc, right? So why Kc? Because Ziegler-Nichols test is conducted on the process, and therefore that proportional controller gain Kp is equal to Kc, and the proportional band formula is 100 by Kp, and therefore it is 100 by Kc. So indirectly, what is given? Critical gain is given, Kc is given, and critical period is given 11.5. So Kc and Tc both are given. Okay. So what is the gain? Critical gain or ultimate gain is 3.33, right? Whereas Tc is 11.5 minutes, and therefore substituting in the formulae from table, these formulae are to be used because it is three mode controller. If it were two mode controller, PI controller, then these formulae must have been used. Okay, whereas sorry, not this one. These formulae must have been used for PI, whereas we want to find out for three mode control, and therefore this should be these formulae should be used. So Kp is to be found out by 0.6, Kc we have found by 3.33. Okay, Ti is equal to Tc by 2. Tc is given to be 11.5 minutes. Td is Tc by 8. So Td is 11.5 divided by 8. And putting in the formula, each formula, what we get is Kp is equal to 0.6 into Kc, and it comes out to be 2. Ti is equal to Tc divided by 2, comes out to be 5.75 minutes, and Td is equal to Tc by 8, comes out to be 1.44 minutes. These were the standard PID controller tuning. Okay. If quarter amplitude criteria is to be satisfied by the settings, okay, then what setting should be used? Which formula should be used? With quarter amplitude one. This formula should be used because it's three mode controller. So Kp 0.6 Kc, Ti, Tc divided by 1.5. In standard it was 2, here TD is same. Okay. Achha. Those settings are not found, I think. You find it and tell me. You find and tell me the values for quarter amplitude. I think I forgot to write. Can you hear me? Tell me the values of for quarter amplitude response. Substitute Kc and Tc in these formulae. Substitute Kc and Tc in this formulae. This and this will be same, only this will be different. Okay. What I can adjust is, okay, controller settings for what? What we are finding? Quarter amplitude response. What are those? AC will be same. KC and KD will be same. Okay. So KC will be equal to, it's same, to formula is same, TI, right? What is TI? TI is equal to PC divided by how much? It's 1.5 instead of 2. Here it is 2, it's 1.5. So tell me this value by calculation. And lastly, this formula is same. TD formula is same. Okay. TD formula is same. So TD comes out to be 1.44 minutes. Okay. Only this has to be found out. And this is 11.5 divided by 1.5. So you calculate it how much it is. Okay. So these are the settings then for quarter amplitude response. Okay. These are the standard settings. These are the standard settings. Okay. So next one, you solve it and tell the answers. Okay. For next problem, you solve this and here only standard settings are asked. Do it and tell me the answer. Just substitute the value of Kc and Tc in the standard mode. For proportional, PI and PID mode. Do it and tell me. Take the pen and calculator, notebook. Find the answers using the table. Shall I show you the table? This is with corrections. This table is to be used. Use this table and find out what are the values. Note down the values of critical gain is 4.2 and critical period is 2.21. Note down Kc is equal to 4.2 and Tc is equal to 2.21. Kc is equal to 4.2, Tc is equal to 2.21. So substitute for P, use this formula. For Pi, use this formula. And for PID, use this formula. And find out the settings Kp, Ti, and Td. Write the answers in chat box. The critical gain Kc is 4.2 and this is 2.21. Let me confirm what is the value of. Yes, Kc is 4.2 and Tc is 2.21. Substitute in the formula, this formula. Okay, and find Kp for Pi, or rather P, Kp and Ti for Pi, and Kp, Ti, and Td for PID. Any answers in chat box? Kp comes out to be 2.1. Devashti has calculated. Yes. Kp comes out to be. Oh. Getting different answers, Swamini. Acha, 1.841. Yes. Anyone else? There are three problems. First is for proportional mode, second is for PI mode, and third is for PID mode. So Kp has to be calculated 3 times, then Ti has to be calculated 2 times, and Td is to be calculated 1 time. Kp for PID, yeah, it's a Pi. This is for PID or Pi? Another Kp 1.89. That's Swamini I think has calculated. This is for Pi, no? Okay. What about PID? Achha, PID Swamini has calculated 2.52. Okay, okay. Yeah. For first it is 2.1. For second it is 1.89. Third it is 2.52. Right. What about Ti for Pi? Proportional plus integral. Ti is it 1.841? Is it for Pi? Okay. And Ti for PID? Okay. So let's match the answer then. Yes. For P mode, Kp is equal to 2.1. Pi mode, Kp is equal to 1.89, and I'm getting 1.84. Yeah. Okay. You are also getting the same. For PID mode, Kp is 2.52, Ti is 1.11, and Td is 0.28 minutes. I think everyone is getting these same answers, right? Okay. Yeah. So let's continue then. Okay. This way the problem has to be solved. So these tables you have to remember. If a numerical problem is asked on this, you must be able to remember these values. There are 4 tables in all. Okay, Ziegler-Nichols method, 2 tables for standard settings and quarter amplitude response settings. Similarly, this method, transient response loop method, standard settings with rather this is quarter amplitude settings and this is standard setting. So in both cases, open loop transient response method and Ziegler-Nichols method or ultimate cycle method, there will be 2 tables each, one for standard PID settings and second for quarter amplitude PID settings. Okay, so all formally you have to remember if the numerical problem is asked on this part. Okay, so let's continue then. So Ziegler-Nichols method is over then. The steps may also be asked, procedure may also be asked, so you should be prepared for that also. Okay, and the third method is frequency response method. Okay, so this we are familiar with. We have studied this. Okay, but we have just to apply it. So this method is based on application of Bode plot. Okay, in control systems, we have studied polar plots, Bode plots, Nyquist plots. Okay, so here we use Bode plots. Okay, so a process has various components. Okay, there is a sensor, there is a controller, there is a feedback element, there is process itself. So each and every component has its own transfer function, right? And then overall transfer function of the system can be found out by cascading this. Okay, transfer function of the sensor cascaded with the controller, cascaded with the process, cascaded with the feedback element, and this forms a complete loop. So we can have an open loop transfer function without feedback or closed loop transfer function without rather with feedback. Okay, so the transfer function is to be known first, and then from transfer function we draw the Bode plots for the open loop. Okay, Bode plot for open loop transfer function, disconnecting the feedback, and from that we decide the PID settings. So today let's know about what criteria should be applied. Okay, so this method, Bode plots are given for the process and control loop, and then tuning of the controller is done. Okay, what are the Bode plots? There are 2 types of Bode plots. We already know, and these plots, are plotted or rather drawn on semi-log papers. Okay, on x-axis it's the log of frequency. Okay, log of omega, and in first plot it's gain versus log omega, whereas second plot is phase versus log of omega. So 2 plots are shown here. The angular frequency log of omega 0.01. Let me maximize it on this current. Okay, look at the x-axis. We have 0.01, 0.1, 1, 10, 100, and so on. Okay, so this is logarithmic scale for angular velocity, which has unit of radians per second. Omega in log omega in radians per second. Whereas this plot is the gain frequency plot. Okay, open loop gain, and on this axis it is log of omega. On this axis it is gain. Gain can be plotted in absolute values or dB values. Okay, it's 20 log of absolute value. Gain in dB is given by 20 log of gain absolute value. Okay, so here gain is given in dB, right? 1. No, I think it's absolute values are given, right? 1, 5, 10, 50, 100, and so on. 100, 200, and so on. Okay. So a typical Bode plot is given, whereas the lower part gives frequency, log frequency versus phase. So this is gain plot and this is phase plot. Okay, we have many times done this in control systems. Okay, so similar plots are here. I won't explain the procedure to draw this one. Just understand that this is the Bode plot for a given system. This is the open loop gain, and this is phase angle. Okay, versus frequency. So as the frequency increases, 0.11, rather 0.01, 0.1, 1, 10, 100, and so on. Okay, and the gain is varying like this, and then it's going like this one. Okay, whereas the phase angle initially is like this, constant, 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 and when it decreases, so variation from some 0, this is 50, some 40 to final variation up to greater than rather 200 or something like that, 210, right? So phase varies from 40 to 210, and gain varies from approximately this is 20, so it must be 18 or something like that, and it varies from this to zero point 0.1. Okay, so these are the absolute values, not in dB. So what must be the criteria then? Okay. Here the stability criteria should be used. Okay. So what is the stability criteria from frequency response or Bode plot? A system is stable if the phase lag is less than 180 at a frequency for which the gain is unity. And the second criteria, system is stable if the gain is less than unity at a frequency for which phase lag is 180 degrees. Okay. So the phase lag should be less than 180 or unity gain, and gain should be less than unity for the frequency or rather phase lag of 180 degrees. So frequency corresponding to this is called as phase crossover frequency, rather gain crossover frequency, and this is called as phase crossover frequency. So let's go to this one, and the gain crossover frequency is marked here, where the gain is unity. The frequency at which the gain is unity is called as the gain crossover frequency, and this margin is called as a phase margin. Whereas the phase plot, where it crosses 180 degrees, minus 180 degrees, this is called as the phase crossover frequency, and the gain corresponding to, okay, corresponding gain is called as gain margin. Okay, so phase margin and gain margin are measured, right? And if both phase margin and gain margin are positive, then the system is stable. Okay, let's see. Okay, system is stable if the phase lag is less than 180 at a frequency for which the gain is unity. So this is the frequency at which the gain is unity, and the phase lag here it is minus 180, whereas it is somewhere 140 or 142, or rather how much? This is 140, right? So slightly greater than 140. So about 38, 37 degrees. Okay, is the difference between 180 and rather 137, whatever it is. So this margin is called as a phase margin. Okay, so it should be less than 180. If this is at 180, that's limiting case, first end oscillations, right? Whereas if the gain crossover and phase crossover match, the system is marginally stable. Okay, if gain crossover frequency and phase crossover frequency are matching or coinciding, then the system is marginally stable. Okay, if the gain crossover frequency is prior to phase crossover system, okay, less than phase crossover, gain crossover is here 0.5 and phase crossover is greater than that. In this case, system will be stable. If the gain crossover is later than after this phase crossover, then the system will be unstable. Okay, so this is what is said here. The system is stable if the phase lag is less than 180 degrees at unity gain, whereas system is stable if the gain is less than unity, okay, for a frequency for which the phase lag is 180. Thus, if the gain is slightly less than 1 when the phase lag is 180, system is stable, but the gain is slightly greater than 1 when the phase lag is 180, then the system is unstable, right? So, for a stable system, what it means that both gain margin and phase margin should be positive. If anyone is negative, system will be unstable. Okay. So the revised stability criteria in terms of gain and phase margin that is commonly used, not the limiting values. Limiting value is gain margin is exactly equal to 1, and the limiting value of phase is 180 degrees. Okay, so those are not used. Generally, commonly used margins for practical cases are the following. If the phase lag is less than 140 at unity gain frequency, system is stable. The phase margin, that is the phase margin, should be 40 degrees at least 40 degrees phase margin. Okay, so phase margin should be 40 degrees minimum, and those are then used for a stable system. Okay, if the gain is 5 dB below the unity, that is absolute gain of 0.56. Okay, this is in dB, absolute gain of 0.56. So it should be less than 1 no? At phase crossover, right? So 0.56 is less than 1. Okay, and here it should be less than 1 for rather 180. So it is 140 phase lag. Okay, so phase margin of 40 degrees and gain margin of at least 5 dB or absolute gain margin of 0.56. Okay, at the crossing of 180 degrees, the system is stable. That is, gain margin should be at least 5 dB. So for practical systems, the phase margin should be 40 degrees minimum and gain margin should be 5 dB. Okay, so gain corresponding to 5 dB is absolute gain 0.56. Okay, so this should be the values of gain and phase 140 degrees and 0.56 absolute value. If these two criteria are satisfied, then the system is stable. Okay, so what is our task? Our task is we will plot the open loop. We will find the open loop transfer function of the system with all components like sensors, transducers, then signal conditioning circuit, then controller, then process, final control element. So all these are taken into consideration, and everyone's each transfer function is found out. Then overall transfer function of this process, open loop transfer function is found out by cascading this, that is multiplying the transfer functions of each, and we now have the open loop transfer function, the whole system. Okay, and then we draw the Bode plot for the given system. We observe the Bode plot and find the gain and phase margins. Okay, so if those gain and phase margins are satisfying these criteria 5 dB and 40 degrees, then the system is stable. If it is not stable, then what should be done? We have to adjust the values of Kp, Ki, and Kd. That is what is the tuning of the system, tuning of the PID controller. So the values of Kp, Ki, and Kd are adjusted in such a way that the gain margin of 5 dB is obtained, or absolute gain of 0.56 is obtained, and a phase margin of minimum to be 40 degrees is obtained. Unless and until this is obtained, we change the values of Kp, Ki, and Kd for our given PI or PID controller. So that's what meaning of tuning is. Okay. So finding the values, rather drawing first the Bode plot of the system, right? Drawing the Bode plot, finding the phase and gain margin, and if they are not satisfying the criteria of this minimum gain margin and minimum phase margin, then adjusting Kp, Ki, and Kd to get or to satisfy this criteria is what is the PID controller tuning. Okay, but the concept then? Here is an example then. Okay, determine whether the following system is stable or not. Right? See the gain plot, open loop gain, right? And see the phase plot. Is it visible to you? Can you clearly see this? Let me know answer. Is it visible clearly or not? Okay, it's visible. Someone is asking Deshti. He's asking that when will we get our unit test marks? Unit test marks again, they were visible to you, no? Unmute and tell me. I made it visible at the end of the test when you submit.
Sir, I didn't saw it. That's why.
Acha. Okay, I'll check and tell you then. Otherwise, it will be visible at the end of this, right?
Thank you, sir.
Okay. Okay. Look at this and tell me whether the system is stable or not. Find the gain margin and phase margin from this and write in chat box whether the system is stable or unstable. Observe it and tell me whether the system is stable or not. What is the gain crossover frequency? This is gain crossover, unity gain. Okay, absolute value. If it were in dB, then log of 1 would be 0. So x-axis, rather y-axis, dB axis would start from 0. Do you get it? Okay. So unity gain has absolute value, whereas if it were in dB, we could have would have taken 0 dB crossing frequency, right? It's absolute value gain, and therefore unity gain crossing is at 0. This is 0.1, this is 0.2 radians per second. Okay, so gain crossover frequency is 0.2 radians per second, and the phase angle corresponding to this from 180 to this, how much this is? Somewhere where it is crossing, I think at 100. Okay, so at 100 it is crossing, phase is crossing at 100, 180 to 100, 80 degrees is the phase margin corresponding to gain crossover frequency. What is phase crossover frequency? Where the phase curve is cutting or intersecting minus 180, it is at This is 0.1, 0.2, 0.3, and 0.4, right? So 0.4 phase crossover omega PC. This is omega PC and this is omega GC, gain crossover. Omega GC is 0.2 radians per second. Omega PC is 0.4 radians per second. And the value of gain corresponding to this, how much it is? This is 1. And how much this is then? This is 0.5, 0.6, 0.7. Okay? 0.9, 0.8, 0.7. 0.7 or 6, something like that. Okay? So, phase margin and gain margin slightly 0.6 or less than that. Let's see how much it is. Okay, first phase margin at unity gain, that is omega GC. Okay, unity gain occurs at 0.15. Yeah? 0.15, the 0.15. No, this is 0.5. This must be 0.4. This must be 0.3. 0.2. This is 0.15. Sorry, this one is 0.15. Okay, so unity gain occurs at omega GC is equal to 0.15 radians per second and phase angle is minus 120. So the first criteria is satisfied, it is less than minus 180. So phase margin is 180 minus 120, that is 60. And for a stable system, phase margin should be greater than 40 degrees, our criteria. So as far as the phase margin is concerned, system is stable. Secondly, the phase crossover frequency is 0.3 radians. This is 0.3, right? 0.5, 0.4, and 0.3. So this is 0.3 radians per second. Omega PC is 0.3 radians per second, where the gain is 0.7. The gain is 0.7. But according to our criteria, gain, absolute gain should not be greater than 0.56. Okay, so system cannot be stable as far as the gain margin is considered. Okay, so gain has to be reduced from 0.7 to at least 0.56, which will correspond to 5 dB, right? So gain margin criteria of 0.56 or less is not satisfied, and the controller gain has to be reduced. Very interestingly, when we tune the PID controllers, okay, each and every component in the process control system has its own gain. Like sensors have their own gains, the transmitters have their own gains, then the controller has its own gain, process, final control elements, process, feedback element, everyone has their own gains, right? And except for controller, all gains are fixed. Okay, when we employ certain sensor or transducer or transmitter or final control element or a process or feedback element, they are fixed. Their gain is also fixed. The component of which we can change the gain is the controller only. Okay, by changing KP, KI, and KD, right? So only the controller gain can be adjusted. So that's why we tune the controllers so as the overall gain, okay, open loop gain of the process control system should be at least 0.56 or less than that. So controller gain has to be reduced from 0.7 to 0.56 or less than that. Is the concept clear then? Okay. how to use this for stability. Tuning is still not done. Okay, we have not done with the tuning. Okay, how to adjust KPKI? What are the formulae for that? That we have not yet discussed. But for stability, if the Bode plots are given, how to find the phase margin and whether the system is stable for these gain and phase margin. That only we have discussed. Okay, we'll stop here today, and the actual tuning will be the last lecture for this chapter. Okay, PID controller tuning. Okay, so in next lecture we will end up with this chapter then. Okay, and we will start then with PLC controllers. Okay, PLC systems. So that's it for today's session then. Okay, let me mark the attendance. So thanks Tim. Ending of the meeting then. You can leave.